All right. Hello, good afternoon, everyone. Welcome to physics tutorial. In this video, I intend to teach a very simple but most times students consider it to be complex. And the topic is graph. Graph. So we'll be considering graphing. Now, I discovered that this works everywhere, not just necessarily for students who are in science and mathematics. If you want to be a sailor, you have to understand your path through a sea. You want to be a pilot, you have to understand the geography and all of that. And all of these things can be explained on a graph. So what is a graph, right? So I want to learn how to plot an accurate graph, how to plot an accurate graph. And the only problem that students find in graphing is what we call scaling. Meanwhile, so what is a graph? Now, a graph is a two-dimensional representation of any model. All right. So you can represent the ground on a graph. You can represent the longitude and latitude on a graph board. You can basically do almost anything that has to do with axis, because you discover that in our contemporary world we are bound by lines and axes. The screen of your phone is bound by line and axis. It's the intersection of axes that gives you dots or points, and when you congest those points, you'll be able to bring out a perfect image. So graphing is quite important in all respects or all aspects. So let's look at that. Now, the first thing we're going to consider in graphing is what we call scaling. Now, scaling helps us to reduce, right, to bring or compress the the the, the what we have in real life to what can be entered into this paper. So you can believe me that you can plot anything on this graph, you can plot anything on this paper, provided the fact that you have a proper scale. Provided the fact that you have a what? A proper scale. Now let's try. Now scaling. If you want to scale, first of all, you should know that a graph consists of two axes. Two axes. The first axis is the horizontal. Horizontal. The other axis is the what? Is the vertical. Axis. Axis. Now, basically in mathematics, the horizontal axis is called the x-axis. The vertical axis is called the y-axis. But this is not their original names. Their names are what? Vertical axis and what? Horizontal axis. So come back here. Now these lines going from my left towards the right there, they are called horizontal axis. And according to the graph called it x-axis. Then on this path, you see your vertical axis, and the graph calls it what? Y-axis. Okay. So if you want to plot a graph, depending on the range of values, the first thing you need to do is to consider a scale. What is the representation of my scale? What's the representation of my scale? Take for instance, now I want to plot a graph. Let's just do an instance. So let's assume I want to plot kilometer, right, against time. So this is distance against time. The graph of distance against time gives us velocity. So let's assume I want to plot kilometer against time. And the maximum I have here is 1,000. Then probably maybe let's say 890 kilometers. And I have maybe 720. And let's say I have 640. And I have 530. Right? 1, 2, 3, 4, 5. Let's make use of this. And then between here and here, the highest probably I have here is 5.2. This time is in let's use hours. This time is in hours, like so 5.2 hours, then 4 hours, 4.0, 0 hours, let's do 3.87 hours, let's do 2.19 hours, and let's do 1.30 hours. Now, These are values that you want them to be represented on this plane. The mistake that some people make is they take these values as they are and then assume a 0 point and then take 530, put it here, take 640, put it here. But before then, you need to understand how this thing works. Now let's explain what a graph is. Now there are graphs that are in two colors, green, some are in red. I think there are purple graphs too. But the color is not the problem. The most important thing is understand the plane. Now, if you check, this is a red axis graph. Now, between here and here, there are 10 boxes. Between here and here, 10 boxes. So this is a complete square, 10 boxes, okay? Now, these boxes are consistent with your meter rule. You take a meter rule and measure this. 5 boxes of this graph is equal to 1 cm. So if you understand what I just said now, that means each of these major red boxes, this is a 2 cm, this is 2 cm, this is 2 cm, this is 2 cm, 2 cm, 2 cm, 2 cm across. But just 5 boxes, 1, 2, 3, 4, 5 boxes of this is equal to 1 cm. So whatever you are putting here should be equal to 1 cm. That is the first thing you should understand about scaling. That for each of these 5 boxes is equivalent to what? 1 centimeter. So from here to here is 2 centimeters, so 4 centimeter, 6 centimeter, 8 centimeter, 10 centimeter, and so on. Now look at this. This is 1,000 kilometers, and we want to represent it upon this. Now we are plotting kilometer, which is supposed to be on the vertical axis, against time, which is supposed to be on the horizontal axis. So first of all, you need to have a reference point or your origin called 0. So let's call this place by 0. The reason why I said this is my 0 is because I know I have enough space to get these values into this. And the maximum value here is 1,000. And you know that 1,000 did not fall from heaven. 1,000 started from 0. So if I start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm nowhere close to the maximum value here. So let me upscale. Let's go to 10, 10. If I do 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. It doesn't go. Let's try 50 because I need to get to 1,000. Right? This is the simplest way I can explain this to anybody to understand. So let's do 50. 50, 100, 150, 200, 250, 300, 350, 400. We are getting close, but we are not there. So 50 did not go. The best thing we can use now is 100. So let's check. 100, 200, 300, 400, 5, 6, 7, 8, 9, 1,000. I think we have made progress. So in order to, let's reduce this 0 to this place now. So we have 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. Now let's label this as this kilometer. Good. Very well. You can see now that I have a 1,000, right? Now let us write this. Remember I told you before that 5 of these boxes is equal to 1 cm, but this graph is structured for 2 cm. So this is 2 cm. So what is going to be my scale? I'll write scale here. You can see there's a position graph of dash a dash against that. Scale, my scale is 2 centimeter. It's equivalent to what? 100 units. It's equal to what? 100 kilometer. This is the simple thing about scaling. So 2 centimeter on my graph is equal to what? 100 kilometer on the ground. Perfect. Now let's check this side. The minimum value here is 1.30 hours. The maximum here is 5.20. So from 0, if I do 1, 2, 3, 4, 5, fine, it's going to go. Right? So let's just do that. So here is 1, 2, 3, 4, and a 5. So let's call this time in seconds. The same way. Now this is our scale of y-axis. Our scale of the x-axis is the same, 2 centimeter to what? 1 hour. So on my y-axis, 2 centimeter on my graph, is equal to 100 kilometers on the ground. And my x-axis, 2 centimeters on my graph is equal to 1 hour on the clock. Simple and short. So how can we relate these two quantities? Now, I want to proceed to plot. The first set of values I'm plotting, we can start from the highest though. 1000 against 5.2. Now, how do I locate 0.2 on this line? That is another issue that people have. So let me show you a simple way to do that. Now, we know that this is 0 and this is 100. Between 0 and 100, there are 10 boxes. I need to know the value of each of these boxes so that I can plot a near perfect graph. I might not be able to plot a perfect, but a near perfect graph, right? So how do I know the value of each of these boxes? Now, between 0 and 100, there are 10 boxes. So this is what you do. You pick the first value, 100 divided by what? 10 boxes. 100 divided by 10 is equal to what? 10 units. So each of these boxes is equivalent to 10 kilometers. So let's check. If this is a 0, the first small box, 10, second box, 20, second, next, 30, 40, 50, 60, 70, 80, 90, 100. It makes sense, right? If here was a 10, divided by 10, 10 boxes, you discover that each of these is 1, 1. So because our first value here is 100, we divided it by 10 boxes. It gave us the value of each small box as 10 units. So 10, 10, 10. So that means from here I can have 100, I can have 110, I can have 120, I can have 130, I can have 150. I can find it. So on this line, the same principle. What is here? 1. Between 0 and 1, how many boxes? 10 boxes. What do? Say 1. This is for y. For x, 1 divided by 10 boxes. So let's check. 1 divided by 10 boxes. 1 all upon 10 gives us 0.1 units. So each of these boxes is equal to 0.1. So let's check. If here is 0, the first box 0.1, second box 0.2, 0.3, 0.4, 0.5, 0.6, 7, 8, 9, 1.0. It makes sense. So that means I can have a 1.2, I can have a 1.9, I can have a 2.2. You understand? So this is the closest we can go. Now, assuming I have two decimal like this, 3.87, how do I locate 87? Because this is too small to carry 87, but it can carry one decimal place. So I'll round it up to 3.9. But if you want to get this value perfectly fitted here, you convert this to standard form. So this can be 38.7 times 10 raised to the power of minus 1. You understand? So that you have 38.7 on your graph. When you get it, you can convert it back. But that is too complex. This is just the simplest way for those who want to understand how to plot with one decimal place, because there is no value that cannot be contained in this, as much as your scale is what? Perfect. Even if you give me a billionth value, it's very easy. Just convert the value to a standard number and then plot your graph. When you eliminate your values, you convert it back to ordinary form, and you are good to go. You will have a value that is close to what a perfect computer will give you, right? So let's try and plot this, and then we wrap up. 1000 against 5.2. 1000 against, and this is a 5. So 5, we discovered that each of the value of our boxes is 0.1. So 5.1, 5. So the second box is 0.2. So we are putting, this is our 5.2. Next, 890 against 4.0. So 800, 800, 810, 820, because we said that each unit is 10. So 800, 810, 820, up till 890 against 4.0. Good. Next, 720 against 3.87. 720, 700, 710, 720 against 3.9. Since we don't have an 87, so 3.9 is here. This is 3.1, 0.2, 0.3, 0.4, up to 9. Okay, so 720, 710, 720 against a 3.9. Then we have a 640 against 2.19, 600, 610, 20, 30, 40 against a 2.2. the 2.1, 2.2. So here, 610, 20, 30, 40 against a 2.2. Then finally, we have the 530 is 510, 20, 30 against a 1.3. So we have a 1.1, 2, and 3. So we go 510, 20, 30 against 1.1, 2, and 3. You can see the progression. So this is just a sample graph of how your graph is supposed to be. So when you get a meter rule and you plot your graph, there's something we call the line of best fit. Yes, these are common things we are going to observe while plotting graphs. So line of best fit. So you will check which of the lines fits properly. And especially when the graph is here, you are told to start the graph from the origin, regardless of how your points are. Make sure the line of graph passes through 0 from the origin and draw the line of best fit. But obviously, this graph is looking like it's going to have an intercept. But again, because it is a kilometer against time graph, it is not supposed to have an intercept. So take this as an example. I'm not going to draw the line because it's going to give us an intercept. All right. I just use these values formulated now to be able to give us a good picture of how to plot a graph. I want to believe that with these short words of mine, these little videos I just made now, you will be able to plot a perfect graph. So please, if you have any questions, any comments, you can just pass it and we'll check it and answer you. Thank you so much for participating. Have a nice day.